Hello, everyone. Welcome to today's presentation. I'm excited to have you here. Today, we're going to explore the fascinating world of light and how it travels. The title of our presentation is Light and How Does It Travel in a Straight Line? We'll cover the basic principles of light, how it moves, and why it travels in straight lines. So, let's get started and discover the amazing behavior of light together. Let's take a quick look at the contents of today's presentation. We start with the fundamental concept of light, which is essential to understanding how we see objects. Then, we'll explore reflection and its laws, which explain how light bounces off surfaces. Next, there's an activity focused on reflection and the images formed, helping us grasp these concepts practically. Moving on, we'll discuss real and virtual images, highlighting their differences and significance. We'll also look at how we see objects through different cases, which will introduce us to the roles of concave and convex mirrors. These mirrors have unique properties and uses, especially in various practical applications. Then, we'll delve into the terms related to these mirrors and how images are formed by plane, concave, and convex mirrors. We'll compare these types of mirrors to understand their differences better. Following that, we'll examine the uses of concave and convex mirrors in real life, such as in telescopes, headlights, and security mirrors. We'll also explore the concepts related to lenses, including terms associated with them and their types, like diverging and converging lenses. Finally, we'll cover the dispersion of white light through a prism, which beautifully demonstrates how white light splits into its component colors, connecting back to the broader theme of light's behavior and properties. Throughout the presentation, I aim to connect these points clearly, emphasizing their importance in understanding optics and how we perceive the world around us. Light is a fascinating and essential part of our world. It's a naturally occurring substance that plays a crucial role in how we see and perceive our surroundings. Without light, our vision would be impossible, and objects around us would remain hidden in darkness. The sun, of course, is the primary natural source of light that we rely on every day. Its rays illuminate the earth, making it possible for us to see and navigate our environment. Understanding light helps us grasp fundamental concepts about vision, nature, and even how energy works. As we explore further, keep in mind how integral light is to almost everything we experience visually. When we talk about the traveling of light in a straight line, the key idea is that light moves in a straight path unless something blocks it. To understand this better, imagine trying to see the flame of a candle through a straight pipe. You'll notice that you can see the flame clearly, but if you bend the pipe, suddenly your view is obstructed. This simple experiment shows that light naturally travels in a straight line. We call this behavior the rectilinear propagation of light. Recognizing this straight line movement helps us understand many optical phenomena and is fundamental to how we study light in general. It's an important concept that links to the broader theme of how light behaves in our environment. Now, let's talk about how objects can be classified based on their interaction with light. First, we have transparent objects. These are objects that allow light to pass through them completely, meaning you can see clearly through them. A good example of this is glass. When you look through a glass window, you can see everything behind it clearly. Next, there are translucent objects. These allow light to pass through, but only partially. So you can't see through them clearly, they scatter the light. Think of butter paper. When you place it over a light source, the light passes through, but you can't see through it sharply. Finally, we have opaque objects. These do not let any light pass through at all. If you try to see through an opaque object, like a book, there's no way to see through it because it blocks all the light. Understanding these categories helps us see how different objects interact with light and influences how we perceive the world around us. When light hits a surface, it has two possible fates. It can either get reflected or bounce back. Surfaces that are well polished, like mirrors, are especially good at reflecting light. This bouncing back of light is what we call reflection. Reflection is a fundamental concept because it explains how we see objects and why mirrors work the way they do. It ties directly into the overall theme of understanding light behavior, which is essential for exploring more complex optical phenomena. So remember, Whenever light encounters a smooth, shiny surface, reflection is what causes it to bounce back to our eyes. Let's talk about some fundamental laws of reflection. When a ray of light hits a reflecting surface, we call that the incident ray. The ray that bounces back after hitting the surface is the reflected ray. Now, at the point where the incident ray strikes the surface, we imagine a line perpendicular to that surface. This is called the normal. It helps us measure angles consistently. The angle between the incident ray and the normal is known as the angle of incidence, or I. Similarly, the angle between the reflected ray and the normal is called the angle of reflection, or R. An important rule here is the law of reflection. It states that the angle of incidence is always equal to the angle of reflection, so I equals R. Also, both these angles, along with the normal, all lie on the same plane, which is a key point in understanding how reflection works. To clarify further, AOX is the angle of incidence, and BOX is the angle of reflection. The normal itself is represented as MON. What's interesting is that the reflected ray leaves the mirror at the same angle at which the incident ray strikes it, maintaining this symmetry. Finally, when light rays reflect off a mirror, they tend to either converge or appear to diverge from a specific point in front of the mirror. This point is what we call the image of the object. So, in essence, the way rays reflect forms the basis of how we see images in mirrors, connecting the physical law to the formation of images we observe every day. Let's talk about the difference between real and virtual images. A real image forms when light rays actually cross after reflection, and because of this, real images can be projected onto a screen. Think of a camera or a projector. Those are creating real images. On the other hand, a virtual image is formed when the diverging rays appear to cross, but in reality, they don't actually meet. Virtual images can't be displayed on a screen. Instead, they are seen only when looking into the mirror or lens. Now, focusing on plane mirrors, the image you see is erect, meaning it stands upright, and it's virtual because the rays don't actually meet behind the mirror. Interestingly, the size of this virtual image is the same as the object. Also, the image appears at the same distance behind the mirror as the object is in front of it. This symmetry is a key concept in understanding how plane mirrors work, and it ties into the broader theme of how light and images behave in different optical systems. Let's talk about how we see objects in this case. Imagine a ray of light coming from object A at some point, say point O. The light bends, it's deflected, before it reaches our eyes. Now, here's the interesting part. Our brain can't detect that the light has been bent. It assumes that light always travels in straight lines. So it interprets the incoming light as if it's coming directly from a different point, which we call point B. This means that even though the object is actually at A, we perceive it at B because our brain is tricked by the way the light has been bent. B, in this case, is what we call a virtual image. It's not really there, but our brain perceives it as if it is. The key idea here is that we always perceive objects as if the light rays are straight, coming from these virtual images, even when the rays have been bent or refracted along the way. This concept connects directly to our overall understanding of optics. Our perception is based on how the brain interprets the light rays it receives, regardless of what actually happens to those rays along their path. Now, let's talk about the properties of the images formed by a plane mirror. First, these images are virtual, meaning they can't be projected onto a screen because the light rays don't actually come from the image itself. Instead, the image appears to be located somewhere behind the mirror. In fact, it appears to be as far behind the mirror as the object is in front of it, which helps us understand why the image looks so realistic. The image is also erect, so it maintains the same orientation as the object, unlike some other types of images that can be upside down. Additionally, the image is laterally inverted, which means if you raise your right hand, your mirror image raises the left hand. Finally, the size of the image is the same as the actual object, which is quite useful in everyday situations. These properties are fundamental because they shape how we perceive our reflection and interact with mirrors in daily life. Now let's look at lateral inversion, which is a fascinating aspect of images formed by plane mirrors. When an object is reflected in a mirror, the image appears reversed from left to right. This means that the right side of the object seems to become the left side in the image, and vice versa. It's like the image is flipped horizontally, and this is what we call lateral inversion. A common example you might have noticed is on ambulance vans. The word ambulance is written backwards on the front of the vehicle. This is actually a practical application of lateral inversion. When a driver looks into a mirror or a reflective surface in front of them, the reversed word appears correctly, so they can read it easily and quickly. Understanding this concept ties into the overall theme of how images are formed and perceived in mirrors. It's a key idea because it explains why images are reversed and how we can use this knowledge in real-world situations, like safety and signage. Now let's talk about spherical mirrors, also known as curved mirrors. These are mirrors that are shaped like a section of a spherical surface, meaning they have a curved, rounded shape. There are two main types of spherical mirrors, concave and convex. Concave mirrors are those that curve inward, like the inside of a bowl, while convex mirrors bulge outward, like the back of a spoon. Understanding these two types is important because they have different properties and uses, especially when it comes to how they reflect light and form images. As we progress, you'll see how each type plays a role in various optical applications, linking back to the core concepts of how mirrors manipulate light and images. Let's talk about concave and convex mirrors. When we consider a concave mirror, think of it as a spherical mirror where the outer surface is painted, and the inner surface acts as the reflecting surface. This means the mirror curves inward, like the inside of a bowl. It's important to remember that this inward curve causes light rays to converge, which is why concave mirrors are often used in applications like shaving mirrors or headlights. Now, on the other hand, we have convex mirrors. Here, the inner surface is painted, and the outer surface is the reflective part. This means the mirror bulges outward, like the back of a spoon. Convex mirrors cause light rays to diverge, providing a wider field of view. That's why they're commonly used as rearview mirrors in vehicles or in security areas. Connecting to our overall theme of optical devices, understanding these differences helps us grasp how the shape of a mirror influences the way light behaves and images are formed. So, whether it's a concave or convex mirror, the key lies in which surface is reflective and how that shape affects the reflection. Let's go over some key terms related to concave and convex mirrors. First, we have the pole, or P, which is simply the midpoint of the spherical mirror. Think of it as the center point of the mirror's surface. Next is the center of curvature, or see this is the point located at the center of the sphere that the mirror is a part of. It passes through the mirror's curve and shares the same tangent and curvature at that point, essentially defining the sphere's center. Then there's the principal axis. This is an imaginary line that runs through the optical center and the center of curvature. It's the main reference line we use when analyzing how light rays behave with the mirror. Moving on, we have the radius of curvature, or R. This is the linear distance from the pole, or P, to the center of curvature. See, it helps us understand the size and curvature of the mirror. Finally, the principal focus, or F, also called the focal point, is where rays of light parallel to the principal axis either converge or appear to converge after reflection. This point is crucial because it determines how the mirror forms images, whether real or virtual. All these terms are interconnected and essential to understanding how mirrors work, especially when analyzing image formation or designing optical devices. Keep these concepts in mind as we continue exploring the behavior of concave and convex mirrors. Let's now look at the key differences between plane, concave, and convex mirrors. Starting with the nature of the images they form, a plane mirror always produces virtual images. These images are upright and appear to be behind the mirror, no matter where the object is placed. In contrast, a concave mirror can produce both real and virtual images depending on the position of the object. When the object is between the pole and the principal focus, the image is virtual and erect. For other positions, the image becomes real, inverted, and can vary in size from magnified to diminished. Convex mirrors, on the other hand, always produce virtual, erect, and diminished images, regardless of where the object is placed. The images are always virtual and appear to be behind the mirror, which makes convex mirrors very useful for wide-angle views like in vehicle side mirrors. Now, regarding the size of the images, a plane mirror always produces an image the same size as the object. For concave mirrors, the size varies. Magnified and virtual when the object is between the pole and the principal focus, magnified and real when between the pole and the center of curvature, and diminished when beyond the center of curvature. In the case of convex mirrors, the image is always smaller than the object. Finally, considering the distance from the mirror, a plane mirror always maintains the same distance as the object. For concave mirrors, the real image distance from the mirror decreases as the object moves further away. And for convex mirrors, the virtual image always appears between the principal focus and the pole, at a fixed position relative to the mirror. Understanding these differences helps us see how each type of mirror is suited for specific purposes, whether for image magnification, safety, or wide-angle viewing. Let's talk about some common uses of concave mirrors. You might be surprised to learn how versatile they are. For example, shaving mirrors often use concave surfaces because they can provide a magnified and clear reflection, making grooming easier. Doctors also use devices like ophthalmoscopes, which incorporate concave mirrors to see the inside of the teeth or the eyes with great detail. Headlights in vehicles are another important application. Concave mirrors reflect light inward, focusing it into a powerful beam to illuminate the road ahead. This ability to concentrate light is a key feature of concave mirrors. They gather and focus incoming parallel rays, which is why they're called converging mirrors. Depending on how far the object is from the mirror, the image formed can vary. Sometimes it's real and inverted, other times it's virtual and upright. This property makes them useful in telescopes, especially astronomical telescopes, where focusing distant light is essential. You'll also find concave mirrors in solar furnaces, where they concentrate sunlight to generate high temperatures for industrial processes. And finally, in medical settings, head mirrors use concave mirrors to direct light into a patient's body, providing a focused beam for examinations. Overall, these mirrors are essential in many fields because of their ability to gather, focus, and manipulate light efficiently. Now, let's take a look at some common uses of convex mirrors. First, you'll notice that they are used in street light reflectors. This is because convex mirrors can spread light over a wider area, making street lighting more effective and safer for pedestrians and drivers alike. Next, convex mirrors are also used in sunglasses lenses. They help in reducing glare and improving peripheral vision, which enhances comfort and safety when you're outdoors. Moving on, side view mirrors on vehicles are a perfect example of convex mirror application. They provide a wider field of view, allowing drivers to see more of the road behind and to the sides, reducing blind spots and increasing safety. And lastly, in car repair shops, convex mirrors are used for inspecting hard-to-see areas. Their ability to give a broad view helps mechanics identify issues more efficiently. Overall, convex mirrors are essential in many everyday contexts because of their ability to provide wider, clearer views, which is a recurring theme in their applications. Let's talk about lenses. A lens is basically a transparent medium bounded by two surfaces, and at least one of these surfaces must be spherical. This curvature is what gives lenses their unique optical properties. Now, lenses come in two main types. The first is converging or convex lenses, which bend light inward and focus it to a point. The second is diverging or concave lenses, which spread light outwards. Understanding these two types is fundamental because they play a crucial role in how images are formed, whether in our eyes, cameras, or microscopes. Recognizing the difference helps us grasp the broader concepts of optics and how lenses manipulate light to create clear images. Let's talk about diverging or concave lenses. A concave lens is a type of lens where at least one side curves inward, creating a sort of hollow shape. When both sides of the lens are curved inward, we call it a biconcave lens. Now, these lenses are classified as diverging lenses, which means they spread out light rays that pass through them. Imagine shining a parallel beam of light at a concave lens. What happens? The rays spread out, diverging away from each other. This is a key feature of concave lenses. They cause divergence. If you look at a concave lens, you'll notice the edges are wider than the center, or alternatively, the center is thinner than the edges. This shape is what makes the lens diverge light in that characteristic way. One very practical application of concave lenses is in glasses, specifically for correcting myopia or short-sightedness. They help focus light properly onto the retina, improving vision. So, to sum up, concave lenses are crucial in optics because of their diverging property, and they play a significant role in everyday life, especially in vision correction. Now, let's take a closer look at how images are formed by lenses. When light passes through a lens, it bends or refracts, which causes the rays to converge or diverge, leading to the formation of an image. The key point here is that the nature of the image, whether it's real or virtual, magnified or reduced, depends on the position of the object relative to the lens and the type of lens we're using. Convex lenses, for example, tend to converge light rays and can produce real, inverted images or virtual, upright images depending on the object's location. Conversely, concave lenses diverge light rays and typically produce virtual, upright images. Understanding these principles is essential because they form the foundation for many optical devices, from glasses to cameras and microscopes. So, grasping how lenses manipulate light to form images helps us better understand the broader theme of optics and how we can control light to our advantage in various technologies. Now let's take a closer look at the 7 colors of the rainbow, which are also known as Vibgyor. Starting from the top, we have violet, which is a beautiful deep purple shade. Moving down, we see indigo, a rich dark blue that's often associated with depth and introspection. Next is blue itself, a lighter calming shade that's very familiar to us. Then we have green, symbolizing nature and growth, which is very refreshing to our eyes. After that, we encounter yellow, a bright, cheerful color that exudes energy and positivity. Following yellow, we see orange, a warm and vibrant hue that signifies enthusiasm and creativity. And finally, at the bottom is red, the boldest of the colors, representing passion and strength. These 7 colors, violet, indigo, blue, green, yellow, orange, and red, are what make up the spectrum of visible light. When combined, they form the beautiful, seamless transition of colors we see in a rainbow. Remember, understanding these colors helps us appreciate the natural beauty around us, and also plays a crucial role in various fields like optics, art, and communication. Let's talk about the dispersion of white light through a prism. You might think sunlight appears as just plain white, but in reality, it's made up of 7 different colors. When we pass a beam of sunlight through a triangular prism, or even when light hits a compact disc, these colors become visible. The 7 colors you see are violet, indigo, blue, green, yellow, orange, and red. These are exactly the same colors we observe in a rainbow after rainfall. What's fascinating here is that the splitting of white light into these individual colors is called dispersion. This process helps us understand how white light isn't just a single color, but a mix of many, and how it can be separated into its component parts. This concept is central to understanding the nature of light and how different wavelengths behave differently when passing through various mediums.